hard. So you can just take that sheet out and write them down on this first slide. So the first one is 1 over 1 minus x. What is that in its summation notation? And where does this come from? Like, this is the really basic geometric series one, right? So that's not so much you have to memorize it as you just have to know that this is a geometric series thing, right? Does that make sense? So that would end up being 1 plus x squared, etc. Like if you wrote out what the terms were. If you walked in late, I'll give your quizzes at the end. The second one is e to the x, right? Is that the next on the list? Okay. It is the sum from n equals 0 to infinity, x to the n over n factorial. Remember how back on one of the first days I said, oh, this sum that was like 5 to the n over n factorial from n equals 0 to infinity? I was like, oh, that's e to the power of 5. So you can actually, if I had made this like 2 to the n over n factorial, it would be e squared, right? And you find that by repeatedly taking derivatives of e, which are all e to the x, plugging in 0, which gives you 1, right? That's where that comes from. The other two you have to know are sine and cosine. So sine of, and if you were to expand this out, it'd be 1 plus x squared over 2 factorial, x cubed over 3 factorial, etc. This one had radius of convergence infinity, which you could prove. I think we actually did it in the previous lesson. This one has r equal to 1 because of the whole geometric business. Okay, sine x is, so what did you notice when Caleb computed the formula for sine? What kind of powers did it have? Odd powers. Sine's an odd function. Odd function, odd powers. Yeah, okay. That was, and this one alternated. It's negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So I think it was x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. Its r is also infinite. And then how did you find cosine's series? It's the derivative of sine, which made that x into a 1, right? It made all the odd powers into even powers, right? So cosine's series is the sum from n equals 0 to infinity. It's still negative 1 to the n, but it's x to the 2n over 2n factorial, which would be 1 x squared over 2. Oh, that should be a minus there, sorry. Minus x squared over 2 plus x to the 4th over 4, etc. Its r is also infinity. Those are the ones you have to recognize and memorize. But I don't think the first one's not hard, right? And the third and fourth are related to each other, yes? And so then it's just e, really, that you really have to know. The other ones you have to be able to like recognize them and use them given like on a written homework. If you sort of see something that doesn't involve a 2n plus, it's just 2n plus 1 and not factorial, that's arctan. So for the other two to use them, but not memorize them.
Is that an infinity with cosine?
Yes, the last one is infinity. And remember that when you take an integral or a derivative, the r doesn't change. It's just the endpoints that might. And so if your r is infinite and there's no endpoints in that interval, same interval radius for the next thing. Okay. So you can use known power series to get power series for related functions. Like we did this with the geometric stuff, didn't we? We find the geometric series for one thing and multiply the coefficient sort of in, right? So arctan of x. If you walked in late, I forgot to print these notes. You guys got to write them on blank paper because, like, I'm a ditz and a half. I'm so sorry. If you need scratch paper, there's some right there. Okay? This was on your notes, so just write down. N equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. That's the formula for arctan. All right, so how would you handle the whole just the arctan of x squared thing? Leave the x to the fifth off the front for now. How would you handle this x squared? What would you do with that x squared? Enter it in for x. So that becomes x to the fifth times the sum from n equals 0 to infinity, negative 1 to the n, x squared to the 2n plus 1 over 2n plus 1. What happens to those exponents inside of your summation? They multiply, good. And when you multiply the 2 and the 2n plus 1, what do you get? 4n plus 2. And then finally, how do you take care of that x to the fifth? Multiply it in, and then what happens to the exponents? They add, very good. Oh, that should be a negative 1 to the n, x to the 4n plus 7 over 2n plus 1. But the point is that once you know Maclaurin series for certain things, don't use the definition to rederive others. Do you see what I'm saying? Like the definition is to use the derivatives, right? And plugging in 0 into those derivatives. But if you know how to find already know arctan series, you don't have to redo that process. That's all.
Are you going to get a cheat sheet for that?
As I said before you walked in, you have to know the first 4 on that list you didn't fill in last time. The 1 over 1 minus x, e, sine and cosine, arctan, just you'll put in homework because, you got to know them all in homework. Okay, the next one is ln, right? Also one that you don't have to know. So I think that we had a formula for ln of 1 plus x. Is that the one that you did out, Caleb? Yep. And your book defines this one to begin at 1. Negative 1 to the n minus 1, x to the n over n. So that's the formula for ln of 1 plus x. Also one you don't have to memorize, just be able to use it.
What? I know it defines it at 1. I was like, why does it start at 1? Then I realized it's a natural order.
And it's because when we did this one, we actually re-indexed it to make it start at 1. All right, so x squared, when you deal with this ln part, what gets plugged in for x? X cubed. So you have the sum from n equals 1 to infinity, negative 1 to the n minus 1, x cubed to the n over n. So what happens to the 3 and the n?
Multiply.
And then what happens to the squared? Adds. So you have the sum from n equals 1 to infinity, negative 1 to the n minus 1, x to the 3n plus 2 over n.
Give me like an extra credit where you have to memorize the 3 that we were supposed to memorize.
If it's an extra credit question, it probably won't be that, but it might be like to rederive them, like to use the stuff like where they came from. Both arctan and ln were done in section 11.9 where you use derivatives and integrals. Remember that? We had to differentiate a series or integrate a function. They involve geometric stuff. Like we did both of those in section 11.9. Okay. So that's how you use a known series to find a series for a more complicated thing. We'll discuss even more complicated ones for which you can't even find a great closed form pattern. You just find the first few terms and just move on with your life. Okay. So pretty sure that on Friday you focused a lot on Maclaurin series, right? Which meant that what were you plugging in for your A value? 0. So there's the whole general Taylor series, which we have to discuss a little bit more today. So who remembers what the whole general pattern was for these coefficients? Do you remember that? Fn at A, so that's the nth derivative at A over n factorial. And that came from trying to make the function match at all that function match at the point, the first derivative match at the point, second derivative match at the point. That's where all those things come from. And when you have just a general A and A is not 0, this is called the Taylor series. What about if A is equal to 0? What's it called then? Maclaurin. And all the things in that table that you got, those are all Maclaurin series. So we'll talk about how to find some Taylor series today as well. Okay, and of course you can find these notes online so you can print them off or see the boxes and stuff. So let's.
Do that, or are you going to print them off on Wednesday?
I'll print off a blank copy for you and bring them on Wednesday, and you can choose to fill them in as you see fit. Okay, all right, does that make sense? So find the Taylor series of f of x equals 1 over x centered at x equals -3. So the best way to start this process is just to find a whole bunch of derivatives. And if I'm going to make use by, from first principles, I'll give you a pretty easy function to differentiate, like this guy. So our function f of x is x to the negative first. What's the first derivative? Don't fail me now.
-1 over x squared.
Yep, let's leave it as -1 x to the -2 because we're going to keep going, but that was not wrong. Okay, somebody else, don't fail me now. The second derivative is
X to the -3.
2x to the -3rd,
Oh, right.
right? Does that make sense? And often with these, if you're looking for a pattern, it's easier not to multiply stuff together. I mean, like the negatives, it's fine, but like in the next derivative, the third derivative,
That's negative 6x to the negative.
can I leave it as -2 times 3x to the -4 just for now? Because it is actually easier if you don't multiply them. You'll see a pattern. And let's just do the fourth derivative. It's going to be positive again, and it's 2 times 3 times 4x to the -5. So what thing is popping out in front of the derivative? Of n factorial, right? This 2, 3, 4 is 4 factorial, right? 2, 3 is 3 factorial. 2 is 2 factorial, right? Okay, so just predict what would the fifth derivative be?
Negative 2, 3, 4, 5.
-2, 3, 4, 5 x to the -6. They're gonna be, or -5 factorial, right? Okay. So to find the Taylor series centered at x equals -3, you have to plug in. So that formula is f of x equals the sum from n equals 0 to infinity, nth derivative at a over n factorial times x minus a to the n. That's a 0, not a 6, sorry. So you have to figure out what happens what are we plugging in for a into our derivatives then? -3. Okay, so on the side or below it, f of -3 is -3 to the -1, right? What's the first derivative at -3? -3 squared, -2. Second derivative, say it's 2 factorial, -3 to the -3rd. Third derivative is -3 factorial, -3 to the -4, yep. And the fourth derivative at -3 is going to be 4 factorial, right? -3 to the power of -5. Okay. Can you get me a general pattern for the nth derivative at -3? Okay, this part, so first of all, there's a -1 to some power, right? That part's easy enough. Try that. Okay, is it n or n plus 1? We're starting at, the first thing we plug in for n is 0. So if you did n plus 1, let's see, is that right? Then when I plug in 0 for n, I think my first term is negative. Which it is, but I guess what I'm looking at, so you're not completely wrong, is that there's that kind of flip-flopping. Does that make sense? So I think I'm going to leave it as just n, because I'm going to deal with the -3 separately. Does that make sense? So I'm only looking at, I'm ignoring the whole fact that I have -3, these numbers, these -3 that are positive or negative in their power, right? I'm just dealing with just the stuff in front completely. I'm just not going to talk about the negative inside yet. So let's leave it as -1 to the n. Okay, what else is obviously there? Is it n minus 1 factorial? I think it's just n factorial. Because this is the fourth derivative, that's 4 factorial, right? It's the third derivative, 3 factorial. So the factorial matches the number derivative.
Okay.
Does that make sense?
Yeah, I was looking at it was one less than the power, so.
But the power is definitely 1 less. You've got to look at the stuff relative to the derivative number you're on. Okay, so but the power is definitely 1 less. So this is -3 to the power of negative, let's do negative parenthesis, and then I'd say n plus 1. Does that make sense?
Yeah.
Right? Okay, great.
Where does the x even come into that?
Say that again. Where does the x come into that?
Oh,
Well, now,
wait, no, this is just the multiplier, right?
this is the multiplier. Yep, so then this becomes the sum. So then you have -1 to the n factorial, -3 to the negative n plus 1 power, over that other n factorial, which is this thing, and then x minus, what goes in for a? So that becomes +3 to the n. So -1 to the n. Let's make this over -3 to the n plus 1 times x plus 3 to the n.
Is that the exponent to the exponent to the exponent there?
Say that again?
No.
No, there's no exponent to exponent to exponent. So where are you looking at? I'm sorry.
Because you're kind of going up diagonally there.
Yeah, put parentheses around your -1 to the n divided by -3 to the n plus 1.
Yes. How's that? Times x plus 3 to the n?
Yeah.
Okay, there we go.
Sorry, I was confused.
Nope, that's fine. I should use better notation myself.
Do math books get worse in notation as they get more advanced?
They just end up being kind of lazy and terse is all. You can kind of, I don't think my notes are right on this one, so I'm just going to leave this one at this instead of trying to do more. You can probably simplify that negative somehow. Let's see, that we know is right, but I think you can do one more thing. So you got -1 to the n, -3 to the, you can make -3 into -1 times 3. So that could be -1 to the n plus 1 times 3 to the n plus 1. Do you see what happened there, guys?
I'm done with that.
Do you understand that?
Yeah, I do.
That's because -3 is -1 times 3, right? You can raise the -1 to the power and the 3 to the power. And I think, what does that do to your -1? I think it just makes it always negative. Is that true? Are these terms always just negative?
Yes.
Yeah, that is. Okay, good. So this is the sum from n equals 0 to infinity, -1 over 3 to the n plus 1, x plus 3 to the n. And you can actually verify these terms are always negative because whenever you have an odd power, you have an even coefficient, right? whenever you have an even part that makes the -3 positive, right? Which one just stays negative in front? Yeah.
Couldn't you, instead of expanding it that way, have expanded it with the -3 to the first times -3 to the end, and then just divided -1 to the end?
Yes, maybe. Okay, there's in the interest of time, let me think about that in a second, okay, because possibly. Just FYI, the notes, if you look online, the notes have the wrong answer to this problem, okay? I promise. Like I'm looking at them right now. So if you look online, this is wrong in the notes.
Let me
I
down.
found another one that was wrong in the notes.
Let me know and I'll fix it, okay? If you found another one, okay?
From like last week.
Just send us an email and let us know, okay? Not a problem.
I was relying on you and you let me down.
What? And actually, the notes aren't me, okay? The notes, first of all, I'll let you know on this one, but it happens. Everybody makes mistakes sometimes. It happens. Okay, this one's a little bit easier. I like this one better. E to the 3x, centered at x equals 2. I like this one better because the derivatives are easier, and I haven't had enough coffee today. So f of x is e to the 3x. What's the first derivative?
3 is
3e to the 3x. Yay! What's the second derivative? 9 or 3 squared e to the 3x, right? No sarcasm intended in my voice there, okay? Really, not at all. What's the third derivative? 3 cubed e to the 3x.
so on and so forth.
Katel, you's bugging me. I can hear you talking up here. I'm sorry. Have you got a question? Okay, great. If you did, that's awesome though. All right, so now, so did you get the pattern? What's the nth derivative going to be?
3
E to the 3x, exactly. Okay. So what number are we plugging in for x? 2. So f of 2 is going to be e to the 6th. The first derivative at 2 is 3e to the 6th, right? What's the second derivative at 2?
Oh, I see, this can be like that.
So take the second derivative, plug in 2, you get,
18e to the 6th.
if you take this thing and you plug in 2 for x,
So,
3e squared e to the 6.
my bad, I thought you multiplied the entire.
Nope, I fixed that bad. Okay, the next one, you get shh. Okay, what? Yes?
What was the derivative of the first one would be 6e to 6?
No. The derivative of e to the 3x. Chain rule.
She's plugging in the 2 and
You don't plug the 2 in until after you've taken the derivative. Thank you. You take the derivative. You're mixing up your order of operations here. You take the derivative, then you plug in 2. You don't plug in 2 first. Okay. What's the third derivative at 2? Yeah.
Well, that would be 3 cubed e to the 6, but also if you took the derivative of e to the 6, that would just...
It'd be 0. Yeah, everything would be 0. But, so what you're trying to, why are you saying e to the 6? Why do you say that?
Because
2 times 3 is 6.
Let her answer. So I just can't hear you. I speak up. I just can't hear you.
I don't know what I'm saying. I'm confused.
I think what you're trying to do is you're trying to plug in that 2 too soon. That's what the mistake is. You need to take the derivative and then input the number. You don't put the number until you've taken the derivative. So forget that you had x equals 2 for a while, take your derivatives, and then plug in 2. Okay. So this function, your f of x, is going to be equal to that sum from n equals 0 to infinity, the nth derivative at your value over n factorial x minus a to the n. Okay. So what number goes in for a?
So when you squiggle.
2. Okay. And the thing that we just did on the side was figuring out what this nth derivative at a is. So like if you took this thing, that nth derivative, so it would be nth derivative at 2 2b.
3 to the e to the 6.
Do you see how there's always an e to the 6 there? So it'd be 3 to the n, e to the 6th. And this is over n factorial, right? Okay.
Not 3, 2.
Yeah, 3 to the n. And so the way that you figure these things out is you look for a pattern in the derivatives, which hopefully is easy to spot. It won't give you things that are super difficult to spot. And then you plug, you look for that pattern and you plug that in for the nth derivative at a. Okay. And what these things are good for are things like estimating what this function is near this point. Like if you wanted to know what is e to the 3x like near x equals 2, you could use this thing to approximate it. Caleb prepared a program to show you on tomorrow recitations that shows you how these polynomials, like if you just truncate the partial sums, how when you add more and more things in, they approach your function. So you can draw a picture of like sines graph, and then you can draw a picture of adding the first 2 things, the first 3 things, the first 4 things in sines Taylor or Maclaurin series. And you can show that you'll see that as you add more and more terms in, this thing goes closer and closer and closer to the actual sine curve. I'm pretty sure Wikipedia has one of those things too. Like it has an illustration where it adds in more and more terms, and you can see that it gets more squiggly as you add in more things. That's how you do a general Taylor series. Yeah.
So how will that, A on the numerator, e to the 6th, and the x minus, it's x minus 2, not x minus e to the 6th.
Okay, the A, you said the A is equal to?
E to the 6th on the numerator. And
That's not A. A is this value. A is that 2 value. This is what this thing, that's the nth derivative with 2 plugged in. Okay, that's what you get when you plug in 2. And when you plug in 2, you always have this e to the 6th thing every single time. And then you have 3 to whatever power derivative you have. 3 to the first for the first derivative, 3 to the second. So it's not, that's not your A. Your A is the value, your A is the centered value. And then that thing is what you get when you plug that number in.
I was making a mistake for a second, I thought it was f the n multiplied by a,
No, it's after the n with A put in.
yes.
Yeah, input that value. Okay, so the first examples that we had were like just a singular monomial times series, right? Like x squared times arctan. Can you see how something like be kind of like gross? So e to the negative x will have some infinite sum that represents it as a Maclaurin series, right? So does sine, yes? You're going to multiply them, and you have to kind of do like infinite FOIL, okay? Which is why it says to find, but it's a silly thing because FOIL only does 2 by 2, but you have to do infinite distribution in some sense. That's why it says find the first 3 non-zero terms. So the first thing let's do,
You also need to do infinite multiplication rule.
that's kind of, we're gonna kind of reason our way through what are the first few terms in this series, and then call it good enough. Because often, when we did estimations, we like only needed like 3 or 4 things, and it was like a good enough estimate. That's kind of the idea, is to get the first few things, and it might be a good enough estimate. Okay, so e to the x is equal to the sum from n equals 0 to infinity, x to the n over n factorial, right? So what's e to the negative x going to be? How would you get that from e to the x's series? You're going to flip it. What do you plug in for x? Start with that and we'll see if you're right. You plug in negative x. Does that make sense? So we'll input negative x to the n over n factorial. And then what can you do with the negative part? You could just take it out, right? And you'll have the sum from n equals 0 to infinity, negative 1 to the n, x to the n over n factorial. So you're kind of right in that, and this is going to flip-flop. when e to the x of the series does not flip-flop. So let's just write out what the first few terms there are. So if you were to list this out as an infinite, as in like list the terms you're adding, is the first term positive or negative?
Positive.
Positive, right? First term is positive 1. Then when you input 1 for n, what do you get? Is it going to be positive or negative?
Negative.
Negative. X to the first over 1 factorial, which is just, well, so just there's an x there, right? How about when you put n equals 2? What do you get?
Positive.
Positive.
X squared over 2 factorial.
Yep.
Is that just 2?
Which is just 2. Minus.
Skewed over 3 factorial.
Yep. Do you get the pattern from there? Okay. And then,
Sign now, actually.
and let's list out, it's kind of like sine, except for sine skips a bunch of things, right?
Yeah.
So just list out what the things are in sine. They are x, what comes next? Mm-hmm. And then plus x to the, okay, great. Stuff goes on.
Yeah, I can go up to 4 terms with easy.
It doesn't, just, it's okay, yes.
Will we have to prove e2x is equal to x to the n over n factorial, or can we just do the shortcuts and just?
You can just use the formula that you know. That's what you're at. You don't have to rederive it. Yep. Okay, so this function f of x we have is a product of these two things. So what we really have is 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus more stuff times x minus x cubed over 3 factorial plus x the 5th over 5 factorial, more stuff. So we're multiplying these two things together.
There's something that cancels here?
No. But the point is, you only find the first 3 non-zero terms. So it's kind of like, so you can reason your way through it. So start with the 1. First, the 1 would distribute to everybody, right? What's the smallest thing you're gonna get? Like the smallest power?
X in the first.
Just x. Does that make sense? You do 1 times that x, and that's the only thing that's going to be the first power. Because when you distribute the, say, negative x, the smallest powers you get are x squared. Does that make sense? And the next, if you distribute the 1 to this guy, you're going to get x cubed, right? So just think, okay, how am I going to get first power stuff just from 1 times x? That's it. Okay? Now, how are you going to get second power stuff? There's only one way.
Multiplying negative x.
Multiply negative x by that x, right? So that'll be negative x squared. Is there any other way to get second power stuff?
No.
No. Okay.
Is there a rule for multiplying factorials? 2 factorial times 3 factorial?
You've got to just expand out their numbers and multiply it together, like what you get.
Multiplying them together. gives
Like 2 factorial is, 2, 3 factorial is 6. You do the factorial first, then you multiply the answers.
Multiplying them together before that would be killing kittens.
Yes.
Okay.
Okay. Now, how are you going to get third powers?
Could you add them though?
Okay, yes, hold on.
1 times your x cubed.
Okay, so your 1 times your x cubed, so that's going to be minus x cubed over 3 factorial. Is there any other way you can get third powers?
You get x squared first times x.
The x squared times that x. Does that make sense? So plus x cubed over 2 factorial. Is there any other way to get powers of 3? No, every other power is going to be bigger than 3, right? And are any of these terms going to zero out or cancel or anything? No, right? So we're just going to say plus stuff.
Wait, that was our first.
Well, there are first 3 non-zero terms as soon as we do what to the like terms? Just add them together, right? So this is x minus x squared. I think this is 1/6. Oh, I'm sorry, typo there. That should be minus 1/6 x cubed plus a half x cubed. And the important thing about this stuff with powers bigger than 3, right? That's all the stuff with larger powers. Okay, and assuming that you can add negative a sixth and a half in your head, which I definitely can't do at this stage of my life. 3, 6 minus a 6 is 2, 6, which is 1/3. Oh my God, I just did it. So x minus x squared plus a third x cubed plus dot, dot, dot. And with stuff like this, there often isn't a pattern. You're only asked to find the first few terms just to kind of make sure you understand and multiply two things with series that are infinite, that it's going to just be disgusting and ugly and take some care.
Would we get a when does that thing converge?
You won't be asked to do that because I can't give you a general sort of, does that make sense? I don't even know what rate of convergence is. Okay, yeah, I'm not positive. Okay, so that's multiplication. We're also going to do one that's division, just because we have to show you what it's like, okay? I'm so sorry. So, tangent. It sounds so simple, doesn't it? No, I know, you can just shake your heads. It's horrible. Tangent is what divided by what?
Sine divided by cosine.
Mm-hmm.
You're evil.
I'm not evil. I'm just trying to show you all the stuff you're supposed to, know. So x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus, there's more stuff, over 1 minus x squared over 2 factorial minus more stuff.
Is there even a way to oh, you can break them all up.
Oh, no, that would be definitely killing kittens all times infinity. How do you translate something like 127 divided by 3 into division? What's the other division notation? Who goes inside the check mark thing?
127.
3 into 127, like that, right?
Well, you can't break it up by
No.
plus.
No. Okay. So, which thing in the term that we have is like the 127? The sine or the cosine? The sine. Okay, so inside of our division thing, we have x, and I'm going to tell you what those factorials are. This is x cubed over 3, or 3 factorial is 6. Plus x to the 5th over 120. Let's just hope that's all we need, okay? What stuff in that big old fraction is like the 3? The cosine? 1 minus x squared over 2 plus x to the 4th over 24, and let's just hope that's all we need.
Are there times where it won't be?
Hopefully that, I'm not going to give you a nasty one on your homework. It's going to be no nastier than this. Okay, it is pretty nasty, but, not worse.
Web assign randomizes.
Web assign randomizes a little bit, but I'm not sure if there's one on there. So there is, okay. Well, we'll take a look at it. Okay, now first you've got to cancel out this x, right? So what do you multiply this thing by? X. So you have minus x minus x cubed over 2 plus x to the 5 over 24.
Oh, that only gave you one term.
Do you buy that? Okay. Will you just trust my arithmetic?
Yes.
Because you're going to have to get common denominators to do this, like subtracting, right? You should get 1/3 x cubed minus 1/30 x to the 5th. Plus more stuff.
This is death by common denominator.
This is death by common denominator.
It still looks like you're gonna make it.
Anyhow, it's not that bad. What do you multiply the 1 by to make it match x to the 1/3 x to the 3rd?
1/3 x to the 3rd.
1/3 x to the 3rd. Okay, so that'll be 1/3 x to the third minus, it's gonna be a sixth, do you guys agree? X to the fifth, plus bigger stuff, which we don't really care about. Because we kind of just care about who comes next. When you do that subtraction, you should get 2/15 x to the fifth, plus more stuff. And you're almost done. How do you make this one match that 2/15? 2/15 x to the fifth.
Do you even care about what comes out here?
No, because you were only asked to find the first three terms, right? So the stuff that comes bigger is like, power to the seventh and things, right? You have your first three terms. And then what you could do, if you felt like it, or if you needed to for some applications, you could use this polynomial to approximate tangent. There probably are some restrictions as to where you can do that because of intervals of convergence and stuff, but that's kind of the basic idea.
Okay, what I meant by breaking it up, it was not the kitten killing version, it was where the x is over everything and then the negative x to the third.
Oh, yes, that would not be kitten killing, but I don't think it would help.
Okay.
Okay, yeah, you're right.
If I could venture a guess, I think the next term would be 3/60 x to the seventh.
I don't know. You could try. You could do one more, and you could try. But the thing is, that would involve probably some stuff that we skipped up here. Okay, I'm not sure if there actually is a pattern. There might be. I just don't know of it because I haven't really tried. You'd have to go a ways out to look.
And then what was the application of this again?
Well, one application of these polynomials is that you can estimate any function with a polynomial. We're going to do that then on Wednesday and Thursday. So you can use polynomials to approximate a function that's not a polynomial. And Caleb will show you like kind of how that works in recitations as well. And also another application in integrals, like stuff like this, where you can't find an integral any other way. Like, do you know a technique that lets you find the integral of sine to the fourth? Sine x to the fourth?
Yes. Substitution, right?
Nope. Why won't substitution work?
Non-derivative.
You need an x to the third. Yep. Okay, so you find an infinite series for x to the fourth. So that'd be a sum from n equals 0 to infinity, -1 to the n, something to the 2n plus 1 over 2n plus 1 factorial. What goes in for my something? X to the fourth. Okay. And then what happens to those exponents? X to the 8n plus 4 over 2n plus 1 factorial. So,
Take the integral of this.
so that series represents what sine of x to the fourth is. So an application is like, suppose you just stopped at n equals 10. You went from, say, 0 up to 10. And you're going to get a polynomial, and that will estimate what sine x to the fourth looks like. Okay, but what we're going to do is we're going to use it to evaluate this integral correct to 4 decimal places. Okay, so the integral from 0 to 1 of sine of x to the fourth is the same as the integral from 0 to 1 of this whole sum thing. So can you anti-differentiate, when you anti-differentiate this thing, which part is the constant? Everything but the x of this stuff. Does that ring a bell from last time we did integrals in section 11.9? So the -1 to the n is a constant, right? The 2n plus 1 factorial is a constant. It's just the x to the stuff that is the thing you're anti-differentiating. So what's the antiderivative of x to the 8n plus 4 power? X to the 8n plus 5 over 8n plus 5, plus c, but we need plus c in this case.
No.
I should have really had plus c up here, like that's my bad and that's a little bit wrong. But why in this next case do I not need plus c? Because I have a definite integral. Does that make sense? So first we're going to plug in 0, we'll plug in 1, plug in 0, and subtract the 2. Is it clear though why the plus c is irrelevant? Okay. Now when you plug in 1 for x, you see how this x to the stuff is just going to always be 1? What happens if you plug in 0 for x? Like where it goes away, right? So all this is the sum from n equals 0 to infinity, -1 to the n, over 2n plus 1 factorial times 8n plus 5. Does that make sense?
That's evaluatable, right?
Yeah, so what kind of series is this? This is an alternating series. And remember that what you should know is that the AST is one with the sweet remainder theorem. Okay, that's the thing. That's AST is special because the remainder is less than or equal to bn plus 1. Remember that?
Bn plus 1 is less than bn.
Yeah, and we want this accurate to how many decimal places? 4. Okay, so what that means is we want bn plus 1 to be less than 0.1234 zeros and a 5. And what is my bn anyway? One over 2n plus 1 factorial, 8n plus 5.
So we can multiply that out. No, there isn't.
We do go until 45 today, right?
Yeah.
Yeah, okay, so, all right. So, is that okay with that? That's what bn is. Okay, so now to do bn plus 1, you input n plus 1 for n, and don't forget about your parentheses, okay? So it says 1 over 2 parenthesis n plus 1 factorial times 8 parenthesis n plus 1 plus 5, which simplifies to 2n plus 3 factorial, good, times 8n plus 13. You want that to be less than 0.00005. You know what's crazy? N equals 2 is the first thing that works. How do you figure out which n? Well, the only way you know how to do this is you guess and check. I would just start with, you could start with like 2 or 3, but what you do is you plug that number in for n, work out what you get, and see if it's less than this number. There's no way to undo a factorial. So you have to just plug in numbers and see if they give you things that are less than a specific number. Okay? So let me finish, then you ask your question, all right? So if n equals 2 works, what that tells us is that this integral from 0 to 1, that integral represents an area under a curve, right? That's about equal to going up to 2 in that sum. How many things is that actually adding? 3, because if you plug in 0, you plug in 1, and you plug in 2. 0, 1, and 2. So when you input 0, you get 1 over 5, no, 1 over 5, sorry. Stop trying to think. When you plug in 0, the -1 to the n is positive. How about what is 2n plus 1 factorial when you plug in 0? Just 1 factorial. When you plug 0 into this guy, you get 5. Okay. So that's n equals 0. When you plug in 1, your numerator positive or negative? Okay, then 2n plus 1 factorial becomes times I think 13, is that right? And then the last term you need is positive or negative? Plus 1 over n equals 1, this is n equals 2. Yep, 5 factorial is correct. Times 21. And that's about equal to 0.1875763. Okay.
Out to that many decimal places.
Yeah. So
Well, you were-
WebAssign will tell you how many to put in. They're really good about that. And on the homework I specified, I'm pretty sure.
Right, and we were doing it to 4 decimal places, so. if we did-
So WebAssign probably only would ask you for 4 then as well.
There is no way you could make this a test question.
No, I couldn't. But what I might ask you to do on a test is just to do the integration part. Does that make sense? I'll ask you to find the integral, and that's why this is like a take-home quiz question, right? Because I can't make you do it any other way. It's just not possible. So, I think we'll get to example 7, and then I'm just gonna run out of time. So that's kind of like unfortunate. So. And I know the last stuff from the last page isn't officially on the quiz. Okay, so find this thing using a series. So technically speaking, you could do this without the series stuff because you know L'Hopital's rule, right? You have to do it probably how many times?
A lot, at least 3 times.
I think 5. And that would be, and you think about differentiating arctan, like its first derivative already is kind of something that's kind of gross, right? And then doing the derivative of that, and then again, it's going to be really sucky. So here's a really cool way to find this limit. And these are definitely doctored to work out really nice. Okay, let's list out what is inverse tangents, what is its series? And so this is on your last page of the last sheet, but this was a sum, n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1. That's the series for inverse tan.
When class is over, I'm just gonna copy down all the series on the board, Bart Simpson style.
That's probably a good idea. So when in that series, when you input 0, what's your very first term? Like if you take this thing and you put in 0, what do you get when you put in 0 for n, that is? I think you get x. Do you guys agree with that?
Yeah.
Okay. How about when you input 1? Because when you input 0 for n, this becomes x to the first, right? Over 1. How about when you input 1 for n? Is it positive or negative? Negative. And then it's x to the cubed over 3. Okay, who's next? Input 2 for n, you get x to the 5th over 5. Input 3 for x, and you get minus.
X to the sum of those 7.
Do you see there's a pattern there, right? It's like sine's pattern, except for there's no factorials, right? Which does make a huge difference in terms of lots of stuff. All this is over x to the 5th. And so far you're like thinking I'm cheating you and thinking that I'm lying to you, and I'm saying this actually is a good way to find limits because, but what happens when you distribute that 3? So you have x cubed minus 3x plus 3x minus x cubed plus 3/5 x to the 5th minus 3/7 x to the 7th plus more stuff. Something happened to some things. And actually, let's just list one more. The next one would be x to the 9th over 9, right? So I'd have plus x to the 9th over 3, right? What are the kinds of power? The powers that come after x to the 9th bigger or smaller than 9?
Bigger.
Bigger. Okay, does anything cancel? The x cubed cancel? And what else? 3x. You limit x goes to 0. 3/5 x to the 5th plus x to the 9th over 3 plus things that have bigger powers over x to the 5th.
What happened to x to the 7th?
Oh, we also have x to the 7th. I'm sorry. minus 3/7 x to the 7th plus x to the 9th over 3 plus stuff with bigger powers over x to the 5th. So why is that helpful?
Get a 1 on the bottom,
Yeah, so what can you do with that x to the 5th now?
divide.
Divide everybody by it, right? So what's the 3x to the 5th divided by x to the 5th? 3/5. How about the next term? Second, right? Then next we'd get a third x to the 4th, right? Plus more stuff, but that stuff that comes next all has x's in it, right? Can you now plug in your limiting value? Can you now plug in where you're going? To 0. So what happens to everything after 3/5? It's all gone, right? So you just get 3/5 plus big fat bunch of zeros. So, right, 3/5. So
Infinite number of zeros.
those limit questions that you're asked will all kind of involve this same technique. They'll all involve listing out what's in the series, and you should see some major cancellations so that you can actually do division by the thing in your denominator. So, the stuff that we didn't get to is not on your quiz. And just FYI, guys, you wouldn't believe it, but having the quiz after the lesson won. So just, I counted up the votes.